All right, we're going to watch something here in a second. That's one of these things that they call a dropper popper. It's essentially this little rubber thing, it's a little dome that you can flip inside out. And then when you drop it or set it on a hard surface, it flips itself back to the way it was. It kind of inverts itself and it goes flying off up into the air. Okay, so you might see these like you get, at the dentist office or something like that, or in a little cheap treat bag or something at a birthday party when you're a kid. So this is a little slow motion video of it, courtesy of Educational Innovations and the teachersource.com. So they flip it inside out, bam! It flips back to the original position, and it goes flying away as a result. Boom! Put a little ball in there, and once they flip it back inside out, launches that ping pong ball, and it goes flying away. So that little dropper popper toy is a great way to demonstrate stability or instability, which is a huge part of science, especially chemistry. Okay, so in the case of that dropper popper, when we take that little rubber dome and we flip it inside out, we make it a little bit uncomfortable. We stress it. We stretch that rubber in a way that it's not used to being stretched. Okay, when we let it go, all right, it has some stored up elastic potential energy that converts into kinetic energy to flip it inside out. Okay, flip it back to that dome shape that it was before, either launching it up into the air or launching something else like that ping pong ball up in the air. Okay, we started with this little piece of rubber that didn't really do much. If before you go and flip it inside out, it just will sit on your table and stay that way for the next 1,000 years because it'll never deteriorate on its own. But we see this change all of a sudden, and all we had to do was just flip it inside out. Okay, change happens in science as we try and move from a state of instability to stability, or relatively, as something tries to become more stable. Now, objects, atoms, whatever, don't try necessarily, but the nature of physics is for change to happen to make something more stable. It proceeds towards a more stable state. Now, talking about stability can kind of sometimes be weird if you're not used to talking about it like this. So there are a couple other ways we can talk about it. Instead of saying unstable, we might say high energy. Okay, and instead of stable, we might say low energy relatively. The higher in energy something is, the more likely it is to use up some of that energy and release that energy to try and change back to a low energy state. Okay, we can also talk about it in terms of like stress or being comfortable, just to kind of make it a little bit easier to understand. So things tend to like to be in their lowest energy, least stressed, most comfortable, most stable state. It all just kind of going for the same idea. Okay, things like to be comfy, cozy. They want to be stable, not stressed. Okay, and things change when they're not, when they are in a higher energy, more stressed, less comfortable, and less stable state. Okay, change happens in order to try and stabilize things. So that dropper popper is put into a higher energy state when we flip it inside out and build up some of that potential energy, that elastic potential energy. Okay, in that stress state, it is ready to use up that energy and flip back out and go flying away. Okay, so that energy is released. So we go from a higher energy state to a lower energy state. All right. We stop seeing change when something has reached the lowest energy state that it can get to at the time. So in the case of the dropper popper, it would be where the popper flips itself back to the regular shape and then it just lands and sits there. Okay, and this can go for a lot of things. It could be for dropping a ball on the ground and it bounces, 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 and then eventually it stops. Okay, once it stops moving, it's down to its lowest energy state that I can get to in that situation. Now, if you go and push it off a cliff and give it a even lower place to fall down to, then it'll go and fall, and it'll go from, again, a higher energy state to a lower energy state. But then once it reaches the bottom of that cliff, it's going to stop again, and that's going to be the lowest energy state it can reach in that case. So things are always proceeding to become more and more stable. This even works for chemical reactions. A chemical reaction is just atoms rearranging to become more stable. So we have some chemicals that might not necessarily be what we would call unstable. They're not just going to burst into flames on the shelf, but when put near other atoms that it can exchange bonds with, break some of these, make some new bonds, rearrange the atoms. If they can make chemicals that are lower in energy, that are more comfortable, that are more stable, then they will. They'll rearrange, and we get a chemical reaction, a chemical change out of that. And we end up with a release of energy in the process, usually as heat and light and sound, which is why in chemical reactions you a lot of times see a big bang, a flash, you get a color change all of a sudden. You get something very noticeable, a loud sound, because that's energy being released as we go from a higher energy, less stable state to a lower energy, more stable state. So in general, as long as you are watching a change, you are observing something moving or exploding or releasing heat or light, okay, it's in the process of becoming lower in energy. It is trying to become more stable, so to say. Okay, and if something is not changing, that means it's about as stable as it can get in that situation. Doesn't mean it can't be more stable by doing something else to it, but in that situation, that's about as good as it's going to get for there. So we can look at all kinds of stuff in the lab, from everyday objects to chemical reactions, and see that things change based on how they move towards being more stable.
Station 1 is looking at these squishy stress balls. All right. Just as I leave them sitting on the table, they don't do anything. It's good to remember that change happens in science when we're going from a high energy state to a low energy state. And if something isn't changing, that means it's pretty much in the lowest energy state it can reach under these circumstances. Now, if I take one of these stress balls and I squeeze it, okay, I have to really push on it, and I have to keep pushing on it, or else I can feel it push back and reshape to its original form. So I can squeeze it and let it go, squeeze it and let it go. Okay, and every time I'm not forcing it to be like this, it returns to be like this. It changes back into this shape. This is station 2. We're going to look at this slinky first. So when I let it go, it drops, basically hits the floor, and then it doesn't quite reach the floor each time. It's getting a little bit higher. It also doesn't reach back to that highest peak it made it to. And if we let it go for long enough, it's going to keep slowing down. It's going to wind up somewhere around there. Now, of course, it won't do this forever, so you can kind of imagine where it's going to wind up, looking at kind of where it's bouncing in between, if we were to kind of wait long enough for it. Right, here's our pendulum that has some similarities here. So if I get it swinging, it kind of reaches out to about there at first, but as it continues to move, it's going to slow down. So you can kind of imagine where it would wind up once it's fully stopped. Kind of like where we started. Keep in mind what that means about going from a high energy state to a low energy state. Okay. This two-way ramp is our station 3. We've got just a metal marble there on the center. Now I can grab this and move it to the top here. Now it's not going to stay there when I let it go, as you could probably guess. It goes rolling. So at first it kind of reaches up to those wooden blocks on each side. But as we give it time, it goes less and less up each side. And you can guess where it's going to wind up if we wait long enough. Now, if we're trying to get this to reach that final lowest energy state quicker, then maybe putting it all the way at the top of the ramp isn't going to be the quickest way to get there. Maybe it's going to take too long going back and forth and back and forth. So think about ways we could cut that shorter. What could we do to the ramp or the marble or the way that we started off to get it to reach that lowest energy state quicker than what we're waiting for now? This is station 4. We've got a couple batteries hooked up to some wires. We've also got one of those wires hooked up to this bell here. It's got a loose wire here, and we've also got a loose wire on the end of these batteries here. So I'm just going to bring it a little bit closer and touch them. Okay. So when I make contact and complete the circuit, the electricity runs through and it rings the bell. As long as the electricity is flowing, this taps it and hits it right there. And when electricity is not flowing, it releases. Okay, so getting that frayed piece of wire to hit this multiple times, if I can get it to focus, in quick succession, you can get it to ring really fast. Okay, but as long as I'm holding that connection, that hammer is going to stick onto that bell. Okay, so the question is that going to last forever? Am I always going to keep this forced into a high energy state if I keep it like this? Or is there an end to it? This is station 5. We're going to look at what we call the happy ball, which has got a little happy face on there. The sad ball, which has got a sad face. In this book, we're going to drop them and see how quickly they reach their most stable, lowest energy state. So you can kind of make your predictions about it. And we're going to do them one by one. And if I can do some video editing magic, maybe I can place them side by side. Okay, so you can make your predictions on which is going to settle out the quickest, stop its change the quickest. Let's see, let's start with the happy ball. And hopefully I can put these side by side. Here we go. And I'm going to put it down kind of on the level of the table. Station 6 has its own separate video on YouTube, but essentially this is what's going on. We've got a syringe that we pull the plunger up on to make more room. As we do, the color changes in here. It goes from a dark brown to a yellow. And then as we leave it, okay, after the plunger's been pulled up, we see a change in color on the inside where it goes back to that same dark brown color that we started with. Chemically, this is what's going on. We start with this gas, N2O4, okay? And after we pull up the plunger, it breaks apart into 2 of these NO2 molecules. So this is kind of what it looks like overall. So we end up with each one of these guys breaking up into 2 of these to space out and fill up that extra room we've got after the plunger's been pulled up.